So I edited this meme. So the guy on the top asks, is this rotation or vibration? And then he passes him a note. And he says, it's Rovibration. And he's making a face because he doesn't believe that's a word. Actually, I turned in a paper to a journal and they wrote back and said, Rovibration is not a word. And it absolutely is a word. So you can find, in fact, there's a book, the title is called Molecular Vibrotors. So it's combining vibration and rotation in one word. And that's something that gas phase spectroscopists do. So maybe it's a small niche community. But anyway, he didn't put it on there. He got an F on his paper. So the point is both J and V can change in a transition. And that's what we're going to be talking about today is rovibrational transition. So let's go ahead and get started. So what we're talking about today is rovibrational transition to the combination of vibration and rotation. So we have the vibrational fundamental. We're going from 0 to 1, and the quantum number for vibration is V. And then we're actually adding on rotation. So we have quantum number J. So we have two changes in quantum numbers, change in J and a change in V. So let's look at that. So here we have this vibrational energy level diagram. We see down at the bottom, E0 and E1, those are the vibrational levels for the fundamentals. So we're going from 0 to 1. And we're going to eventually build up a row vibrational spectrum. So down here, if we zoom in, this is what we would see. We would see this energy level diagram, and we would have the ground vibrational state. And we would have the ground vibrational state would have rotational energy levels on it. And so we would have V equals 0 and J equals 0. V equals 0 and J equals 1. So we have labels for every one of these energy levels. And then the next one would be V equals 0, J equals 2. And then I'm only going to show 4 rotational levels. So then the next one is V equals 0, J equals 3, but this goes on and on and on. J up to, hundreds and hundreds. Okay. I don't know of any limit to the rotational quantum number. So that's what we have for the ground vibrational state. Now let's jump up a little bit because we could have the excited vibrational state. So V equals 1. Oh, and here's the energy equation for the J energy levels, for the rotational energy levels. We have this B, which is the rotational constant. And then it's written in this traditional way because when you solve the Schrodinger equation for rotation, you end up with these values of J times J plus 1. And so they just leave it written that way. It's a traditional thing. You could say B times J squared plus B times J, and that would be the same equation, but that's not the traditional way of writing it. So this is the traditional way of writing the rotational energy levels. And notice how the energy levels and those black lines are not equally spaced, right? They go up as J squared plus J. So they're not equally spaced. And then we have the vibrational quantum number equation, the vibrational energy equation, where we have the vibrational frequency. I'm going to go ahead and, I guess make a note here that this is right here. This is nu. And this is V. I haven't found a good font for the, I don't have a good way to change the font in the equation editor for PowerPoint. Okay, so I just want to make sure that you know the vibrational quantum number is inside the parentheses. And it's V plus 1/2. That's the vibrational quantum number. And then that looks like a V in front, but it's really not. It's the Greek character nu. And that tilde means it's in wave numbers. Okay. And we could actually, if we wrote the rotational constant in wave numbers, we could actually have a tilde on that too. So you can see V with a tilde sometimes. And so we go from V equals 0 to V equals 1. And so then we come up, one vibrational unit. And then we have, that's the V equals 1 energy level. And then on that one, we have the rotational levels. So we can have an excited molecule vibrationally that's also rotating. And so we would have the J equals 0, 1, 2, 3. And I want to show you the convention of prime and double prime. If I can move my windows out of the way, I can mark over on that side of the screen. So notice the convention here that the double primes are on bottom and the primes are on top. And this will help you in the lab when we're talking about the different transitions and we have J double prime and J prime. You'll realize that J double primes are the lower level and primes are on the top. Okay. Now, one thing that we need to know before we can find a spectrum down here is what transitions are allowed. So that's where we would use the transition dipole moment, but we could also use symmetry. And so from the symmetry arguments, we can get the selection rules. And these are the selection rules up at the top. So delta J equals, now since we're in rho vibration, in some situations we can have a delta J of 0. Okay. So we could have a delta J of 0 for rho vibration and delta J plus or minus 1. Pay careful attention because it's not plus or minus 3 or plus or minus 5. Okay, those are for the particle in a box. Those were for vibration, but they're not for rotation. Rotation only plus or minus 1, and then sometimes 0. Okay? And then delta V is plus or minus 1. So in all of these cases, we're going from 0 to 1. So the delta V is just our 0 to 1 vibrational transition. But then on top of that, we're going to have these rotational selection rules. So let's look at the delta J equals 0. So I'm going to make those green. So the delta J equals 0 line transitions are going to be green. So we could go from 0, 0 to 0, 1. So 0 rotation, 0 vibration, up to 0 rotation and 1 vibration. So that would be a fundamental, 0 to 1. And then you also have the rotational line, 0 to 0. So that's a particular transition. But if delta J is equal to 0, then we could go from 1 to 1 in the rotation. So we could go from 1 to 1, still 0 to 1 in vibration, but 1 to 1 in rotation. So these are on top of each other. Both quantum numbers are changing. Although delta J is equal to 0 in this case, so they're really not. But the other selection rules will allow them to change. We could go 2 to 2, we could go 3 to 3. So for my 4 energy levels on top and bottom, those are the only 4 transitions that we could have with delta J equals 0. But you could imagine if I had a level 4 or 5 or 6 or 7, we'd have all of those too. And so these would all, because they are, it's essentially the same rotational constant in the ground vibrational state and the upper vibrational state. These are all going to be the same length arrow. Does everybody see that? So 0 to 0 is going to be the same as 1 to 1 or 2 to 2. And so those are going to show up in a particular spot. So there's only going to be one spectral line for all of those transitions. It'll be really intense because we have a lot of possibilities because we have molecules in the 0 vibration or rotational state and the 1 and the 2 and so on. So it'll be a lot of molecules in that ground state that can make transitions. So just probability wise, we have in this case 4 different possibilities to get that same spectral frequency. So it's going to be quite intense. Okay, so let's now talk about the delta J equals plus 1. So what do I mean by delta J equals plus 1? Well, I'm going from, if I start at 0, then I'm going to go up to 1. And I still have vibration going from 0 to 1. So all of these are 0 to 1 in vibration. We're just really looking at the differences in rotation. So this one goes from 0 to 1 in J and from 0 to 1 in V. And can you see that that arrow is a little bit longer than the green one? Yeah. So it's going to be at a higher frequency in the spectrum, and so it'll show up down here. And then the next one, let's go from 1 to 2, and so this one is 1 to 2, and then we have a 2 to 3. You see the delta J's are changing by plus 1 in all of these cases, and these would be where they show up in the spectrum. So they'd be at higher frequency because it's a longer arrow, it's a longer jump. It would not be a longer jump if it wasn't a quadratic dependence upon J, but because the J energy levels are not equally spaced, if I'm going from 1 to 2, that's a longer arrow than if I was going from 0 to 1. And so that's what's causing these spectral lines to get higher and higher in frequency. So these are the transitions shown in the energy level diagram, and these are the spectral lines that we see. So remember, there's a difference between levels and lines. The energy level diagram shows the black energy levels. So those black lines in the energy level diagram are the levels, and the spectral lines are differences. Yes? Okay, so the length of this arrow, so great question. The length of this arrow tells you where on the x-axis it will show up, okay? So since this is the longest arrow up here, then this is the highest frequency transition. The intensity depends upon, in this case, mostly the Boltzmann distribution, okay? And that Boltzmann distribution has in it what's called degeneracy, okay? And so as the rotational levels go up in J, there's a degeneracy term of 2J plus 1. So it gets more and more probable to have molecules in the upper rotational levels because there's more seats. I think of it as musical chairs. And so since there's more energy levels at higher rotation, there's more likely for molecules to be there. But then you also have a temperature effect, which makes it less likely. So in all of these, and you'll see this in the rotational lecture. So if you watch the rotational spectroscopy lecture, you'll see that the Boltzmann distribution competing with the temperature effect. So degeneracy makes it want to go higher in excitation, and the temperature effect makes it less probable. So you have this, this shape to the rotational lines down here. I'll go ahead and talk about it. So in this case, degeneracy makes it want to become more intense. So 2J plus 1 degeneracy. And then you have this downward effect, which is the E to the minus E over KT effect. So your rotational spectra and your Rovibrational spectra have this shape. Now what's interesting about that is notice that there's a temperature effect. And so the shape of these rotational lines and where the maximum is will tell you the temperature of the gas. And that's pretty cool. So this is one way for us to determine the temperature of our atmosphere. So we can use satellites and look through the atmosphere at the sun. So the sun is our source. The atmosphere is looking at sunset and getting a spectrum of our atmosphere at sunset by looking at the sun. The sun is a wonderful source of infrared energy, and that spectrometer on the satellite can get the rotational lines of various species in the atmosphere. Like there's going to be some carbon monoxide, there's going to be some methane, there's going to be these molecules, and their rotational profile will give us the average temperature of our atmosphere. So that's one way to measure the temperature of a gas, is using rotational lines. So did that kind of, I mean, it's more than you asked, Philip, but yeah. Yeah, degeneracy and the temperature effect. Yeah, so Boltzmann distribution contains both of them. So it's the Boltzmann distribution, in this case, it's really governing the intensities. Yeah, and it's the position on the x-axis that is governed by the length of the arrows in the energy level diagram. So since that purple line is the longest arrow, that's the peak that's farthest to the right in the spectrum, because you see the wave numbers increasing to the right. Yeah, so the wave numbers increasing to the right, so the longest arrow will be the furthest right. And I've color coded it too, so we're getting bluer and bluer as we go to the right. Now let's do delta J minus 1. Only for delta J minus 1, we have kind of a problem. We cannot start at 0 because we can't go to negative quantum numbers. They don't exist. So the very first possibility that we have for a delta J minus 1 is to start in the J equals 1 level and at the bottom, you see? So it's got to go from 1 to 0. But we can't go 0 to minus 1 because there are no minus 1 quantum numbers. And I've drawn this yellow because that's red shifted from the green, okay? So this is a shorter arrow than the green arrow, and so it's going to show up to the left of the green. And then the next one is from 2 to 1, and it's even shorter than the yellow arrow. And if you don't believe me, print the notes out and get a ruler. Okay. And then the next one is 3 to 2, and it's even shorter than the orange. And so I've color coded these get more and more red because the arrows get shorter and shorter. And then down in the spectrum, all 3 of these lines would show up there. And we have the same kind of profile on this side based upon the Boltzmann distribution, which is the, probability of being populated in the ground state or the v equals 0 rotational states. Yes. Yes, in the spectrum, the x-axis is the wave number. In the energy level diagram, we just space the lines across. There's really no x-axis in the energy level diagram. It's just energy and energy levels. But I've spaced them out according to their frequency difference. So the spectrum down below, I've put the arrows on top of their peaks. So this is the end of our spectrum. Okay, this is the energy level diagrams, which take into account all of our selection rules. And so all of these are fundamental vibrational transitions. Think about that, fundamental vibrational transitions, okay? Because they're all 0 to 1 vibrationally. And then these are the different rotational lines on top of that, okay? So there's just a lot going on, but that's okay. You're learning some amazing stuff here. This is quantum mechanics in action. We could not explain this spectrum without quantum mechanics, because we have specific spectral lines that we can resolve. And we had, before quantum mechanics, we had no idea what was causing this interesting effect. And we'll see a real spectrum here in a minute of carbon monoxide, and you guys will analyze it in a couple of weeks. And so definitely we'll come back to this lecture to make sure that you understand how to assign the spectrum. Okay, so there's a whole bunch of spectral lines in this spectrum, these individual lines. And so in order to keep track of things, we've labeled them. We've come up with some ways to label them called branches. And so these ones on the low frequency side are called the P branch. I don't know why, I mean, it's like a branch with twigs on it. So this branch of spectral lines with all these different lines on there is called the P branch. And then in the middle is the Q branch, and then on the right is the R branch. So PQR, increasing in alphabet. See, I've got this problem with the little zoom window. I don't know how to do that. Let's see if I can maybe get out of full screen mode. Why did you do this to me? Yeah, there you go. You can see it. Yeah. All right. So y'all see that? Okay. Very good. So left to right, we have the P, Q, and R branch, and that's increasing in frequency. So whenever you have a rovibrational spectrum, you need to look at the x-axis first before you label anything, because it's not always left to right. There's an annoying habit of plotting infrared spectra where the frequency on the left is the high frequency and the one on the right is the low frequency. And so in that situation, it would be right to left PQR. So you always need to look at the x-axis to make sure which is the high frequency side. And the high frequency side is the R branch, and the low frequency side is the P branch. So I definitely want to write that down. The high frequency side is the R branch, and the low frequency side is the P branch. Now that's direct absorption. What we've just shown is direct absorption. Okay. We could also do the same thing with Raman, and so we'll do that next. Okay. One other thing too is we label these individual lines, like in this particular case, the yellow one. We label that with the lower state quantum number in rotation. So this is going to be the P 1. And the orange one is going to be the P2. And the red one is going to be the P3. So we have this this labeling scheme where we have P and then J double prime, or R J double prime. And so if this one, the green one, would be the R0. The blue one would be R1. And then the kind of purple one would be R2. So each individual spectral line has a designation. So we would label all of the P branch lines with P, and we would keep track of their quantum number, their lower state quantum number. We know that if it's a P1 line, we know because it's a P, that means delta J is -1. So we can do that. So with P over here, this P means delta J equals -1. And for the R, delta J equals +1. And then the Q branch lines are not resolved in this spectrum, so we really can't label them. But if you could resolve them, they would be also Q0, Q1, Q2, Q3. But there's really nothing to label because they're all on top of each other in my spectrum. You think, does anybody ever really use this stuff? Yes, absolutely. You know who uses the P branch and Q branch and R branch lines and so on? Communications folks who are dealing with satellite communications. And so when you're sending your signals up to and down from satellites, sometimes they will lock the frequency onto a particular spectral feature in the atmosphere, so that if the transmitter drifts a little bit, they'll lock it back to a frequency that doesn't drift, and these frequencies don't drift. And so they can lock it to, say, the R3 line of carbon monoxide or something like that. They will pick a particular rotational line in the atmospheric spectrum, and they will lock their transmitter to that line, meaning they'll keep track of it. And if the spectrometer or the transmitter starts to drift, they'll push it back so that it's really close to one of these lines. They won't get right on the line because it will absorb the signal. But they'll take that absorption and they'll adjust the transmitter so that it's in between some of these rotational lines, and they have a clear window through which to communicate. So now let's summarize. So this, I've shown you sort of the graphical information, you know, with the energy level diagram and the spectrum. So let's look at the math. Let's look at the transition equation. So this is a summary. The energy equation is both the sum of the vibration and rotational energy equations. And so this is for that energy level diagram. These would be the energies. And it's the energy of vibration plus the energy of rotation. And so if you're going to do the selection rule, I mean the transition equation, then you need to take the differences of these. And now there's some things that this neglects. It neglects the anharmonicity for the vibrational modes, and it neglects centrifugal distortion for the rotation. A molecule can rotate fast enough that it causes itself to stretch. Okay, so if you've ever, gosh, they've taken away all of our merry-go-rounds, our carousels, but if you're ever on there, you feel that centripetal force pushing you out to the outside. Well, that same thing happens to molecules. And so the combined selection rules, which we've discussed already, are delta V plus or minus 1 and delta J 0 and plus or minus 1. And so we could come up with those selection rules, use those selection rules to come up with the transition equations. Now I've given you the answers here, I haven't derived them. And so that would be a great homework thing to do, is to algebraically go from this energy level equation to this transition equation, where you end up with this right here. This is going to be the frequency in the infrared spectrum where that spectral line would show up. And so you see it's a function of the J quantum number. And so if J equals, for for this particular case, for P, the minimum J is J equals 1. So, you know, if you put in a J equals 1 in there, you get a particular frequency. If you put in a J equals 2, you get a different frequency. J equals 3, you get a different one. And then we have the transition equation for the Q branch. And so since delta J is 0 for the Q branch, all of the rotational pieces cancel out and you just have the vibrational frequency. So if you think about that, if you want to know the pure vibrational frequency for a particular vibration, find the Q branch and that will be the vibrational frequency. And perhaps you can see what I'm doing here with this, this middle piece of the equation. You see I'm going from, for the transition equation, I'm going from V to V plus 1. But for the P branch, I'm going from J down to J minus 1. And so for this equation up here, wherever there's a J, I put a J minus 1 and a J minus 1. And I put a plus 1 in for V. And then I subtract this whole energy equation with J and V. And so that's how I would algebraically get to this equation down here. And then for the Q branch, V is still going up by 1. Right, you see that, but then J is not changing, so it's J and J. And then for the R branch, I have V going up by 1. Again, so it's a fundamental, and I have J going up by 1. And so in order to get this equation, I could put J plus 1 everywhere there's a J in this equation, and then subtract this equation where you just have J's. Multiply through, do the algebra, and you end up with this particular result. And so this is, I'll do this for J equals 1, 2, 3, dot, 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 right? So the first P line is P1. And then this is for J equals 0, 1, 2, dot, dot, dot. So here's our spectrum. Let's compare this transition equation to the different branches. So for this R branch line, if we start out with J equals 0, then this piece goes away. So I have the vibrational frequency plus 2B. So for the 0 to 1 transition, I'm 2B away from the Q branch. Everybody see that? You know, if I put in 0 for J, then I'm just 2B higher than the Q branch. And then if I put in a 1, if I put 1 in there for the next R branch line, then I get another piece, I get another 2B piece. And so then there'll be another 2B jump over for the R1 line. And then if I make R2, or J equals 2, then I get 2 units of 2B. And so I would jump over another unit of 2B. So notice my rotational lines are separated by 2 times B, and B is the rotational constant. It's a physical property of the molecule. So if I assign these spectral lines and I take differences between them, I can solve for B. So that's really the goal, is to use our spectrum to solve for that physical constant for the molecule B, the rotational constant. Okay, let's do the P branch lines. If I come in here and I put in a 1 for J, because that's the first quantum number for the P branch side, is J equals 1, I have the vibrational frequency minus 2B. And so for the P1, I'm 2B at lower frequency by 2B from the Q branch. And if I put J equals 2, then I go another grouping of 2B. And if I go J equals 3, I get another one. And so you notice that all those spectral lines are separated by 2 times the rotational constant. And we get that from the transition equation. So this is kind of like this is the slope as it depends upon J. And so if I were to plot these frequencies, let's say I made a table and I had all the J values in a table, and then I had all the frequencies for each of those transitions. If I did the slope of those frequencies with respect to J, I would get this 2B value. And I could divide by 2 and I'd have the rotational constant. And that's exactly what we're going to do in a couple of weeks. So when you get your rotational spectrum of carbon monoxide, you will assign the spectrum, you'll make a table, and then you'll do what we call a linear regression to get those slope values, and you'll solve for B. So let's take a Kahoot. Okay, so the rotational branches in IR vibrational transition are called. I'm not trying to like trick you by calling it vibration. This is row vibration. So the rotational branches in the IR. All right, very good. PQ and R, we just covered that. Now, Raman is delta J plus or minus 2. Okay, so these are going to show up at lower frequency and higher frequency than the PQ and R branches. So the rotational branches in a Raman vibrational transition are, so just think about it. See if you can figure this out. All right, kind of a spread there. Because it's delta J minus 2 and plus 2 and 0, you have O, Q, and S. And the IR is PQ and S. So they already established PQ and S, or PQ and R. PQ and R for the IR. And so then when they did the Raman, they just added O and S. What J values are associated with the row vibrational O10 line? So O10. Remember that subscript is the lower J value. And O tells you what the delta J is. Okay, so the O10, again, the 10 means you're starting at 10. So it has to either be the red or the green. And those are the two most popular answers, so that's good. And then the O tells you the delta J. So since it's an O, it's delta J minus 2. The P would be delta J minus 1. Q would be delta J equals 0. R would be delta J plus 1, so it would go 10 to 11. And then S would be delta J plus 2, so it would go from 10 to 12. What J values are associated with a row vibrational R10 line? So R10 now instead of O10. The music is stressing me out. Yay, very good. So we're starting to catch on. So the 10 to 11, the 10 is the R10, and then R tells us it goes up by 1. What's required for molecules to display rotational lines in their vibrational spectrum? And so this is row vibrational, and I didn't really talk about this in class, but I guess you're just going to guess on this one. Okay, so 3 lucky winners. You have to have molecules in the gas phase to show this pure like row vibrational phenomenon, because they need to be able to freely rotate. If it's a liquid, if it's a solid, you won't see this fine structure because they're jamming into each other and they won't rotate freely. So this is a gas phase phenomenon. That's why I talk about atmospheric research, because we got a gas phase molecules. Even detecting in airports, like sniffing for bombs and so on, there are some techniques that might use row vibrational spectroscopy connecting with gas phase samples in that case, if it's a sniffer. So let's do now the same thing, but a little quicker with the Raman spectroscopy. So we still have the fundamental vibrational transition, but remember the Raman effect uses 2 photons. It's a scattering effect. We have an incident photon, so a green laser hits our sample, and then in Stokes Raman, a red shifted signal comes out. So it's inelastic scattering. The molecule has taken some of the light, some of the energy away from that light. And so then we end up with these vibrational transitions. Now I'm going to show these as up arrows over on the right, but it's really an up and down thing. It's really Raman. So please don't let that confuse you. I'm just on the right showing you the transitions that occur, but really not showing the up and down arrows. So we're just showing these as if they were absorptions, but they're really not absorptions, they're scattering. Now the Raman selection rules are plus or minus 2 in J and 0. And then we're still dealing with fundamental transitions, so delta V equals 1. And so we still have the Q branches. So those have not changed at all. And so we still have that central Q branch line where delta J equals 0. But now we have the S lines. So delta J plus 2. So we go from 0 to 2 now, not 0 to 1. And that's shifted to the right even further because it's a bigger difference, a longer arrow. And then I have 1 to 3. And because I've only got, 4 energy levels shown on either up and down, I can only show 2 spectral lines for the Raman effect. Okay, question? Okay, all right, so then those spectral lines would show up here and here. So I don't have enough to show sort of the Boltzmann distribution like we saw before, but they would show the same kind of Boltzmann distribution. Okay, so now let's do delta J minus 2. And so here we have red shifted from the green Q branch line. We would have, and then further red shifted. So from the 2 to 0, and then from the 3 down to 1. You see, you can really tell that these arrows are shorter, which means they show up to the lower wavelength side of the spectrum. So the Raman, rovibrational Raman, the lines are further apart because we have larger differences between the rotational lines. And then let's look at the, so now this is the O branch. We still have the Q branch, and then this is the S branch. And so as we saw in the Kahoot, this would be the first one would be the O2, and then the O3. And this would be the S0 and the S1. So if we put those designations on a row vibrational spectrum, that would be called assigning the spectrum. So that's a spectral assignment when you assign the quantum numbers to the transitions. I'm going to go ahead and move on so we don't run out of time. So you might not be finished writing that down. But let's jump to the math associated with the transition equation. So we still have the same energy equation. We have new selection rules. So we have delta J 0 plus or minus 2. And then notice what I'm doing here. I'm calculating the transition equations in terms of Raman shift. So this is the difference in the incident and scattered light. Okay, so Raman shift is incident minus scattered. And that's what gives me those differences that I saw in the previous spectrum. So for the O branch, we end up with this difference. And so it looks very similar to the P branch. We've just got we've got a different slope and a little different intercept. The Q branch is the same, so it's still the vibrational frequency. And then the S branch is here. So notice here we have a different slope related to the J value. Okay, so let's look at how that plays out in the spectrum. For the S0 branch, we have a shift over by 6B. If I put 0 in for J and calculate this, I'm going to have the vibrational frequency plus 6B. And then if I put 1 in for the next transition, so notice this equation tells me where those spectral lines will show up. That's what the transition equation does. It tells me what the x-axis is going to be in the spectrum. If I put in 1 for J, I get another 4B. And if I put a 2 in, I get another 4B, and a 3 and another 4B, a 4. So every spectral line is going to be separated by 4 times the rotational constant. Okay. And if I do the same thing with the O lines, this one's a little strange because the first O line is going to be 2. So if I put a 2 in here for J, I have a negative 8B, but then this plus 2 brings it back up 6, so I end up dropping 6b. So it's symmetric around the Q branch. It doesn't look like it will be, but you've got to remember that for the O branch line, the very first J value you can have is 2. And so when I put a 2 in for J, then I end up with this 6b shift. And then if I go down to J equals 3, then I have 12, and then I add 2 back in, so it's only minus 10, which is 6 plus 4. So I have still 4b between the peaks. And if I went down to the O4 line, I'd have another shift of negative 4b. So it would be 4b between each of my spectral lines in the Raman. And if I had assigned all of these, then I would have a spectral assignment. So you can look at these. These are the J quantum numbers that I've assigned on those rotational lines. Okay, so now we have this situation. Hamlet has always pondered to be or not to be. That is the question. Well, in this spectrum, we have the IR and we have the Raman. And so I say that if it's absorption, the answer is 2b. And if it is Raman, it's 4b. So we can use either one of these spectroscopy techniques to determine the rotational constant. So let's end with this. If once I have the rotational constant, and here's the actual spectrum you're going to assign in a couple of weeks. And this is the P branch and the R branch because of the x-axis. You see the high frequencies are on the right. Beware if they're plotted the other way, where high frequency is on the left, then that's the R branch and the P branch. See how they've flipped? Look at the x-axis to know which is which. And so once I know B, this is the equation for B. And look what's buried inside of B. The reduced mass, so I can know something about the identity of the particle, the molecule, or the rotation, the bond length. So R is the bond length. So I can get the structure of the molecule. And that's your goal in the carbon monoxide lab, is to determine the bond length for carbon monoxide. And if you do the lab correctly, you will get that bond length to like 6 significant figures, at least 5. So you will be able to determine the bond length to 0.0001 angstroms. That's amazing. That's 10 to the minus 14 meters, plus or minus. So you'll be able to measure something that precisely. That's pretty incredible. Make life easy for yourself. This is all of the constants that you would put in there if you were going to use grams per mole for your mass and angstroms for your bond length. And so make life easy. None of those constants change. And so like combine all of those constants into one constant, and then you can have this where you have the units that you want. Notice whenever you're doing something with all these constants, you want to use all the significant figures that you can find in the literature so that you don't introduce rounding errors. So use Planck's constant out to, 7 decimal places. Use Avogadro's constant out to 7 decimal places. The speed of light has 8 significant figures. I mean, it's a defined constant, so it has an infinite significant figures. But yeah, this is definitely note card based, because if I give you the bond length and the reduced mass, you can find the rotational constant, and you could simulate the spectrum by drawing peaks. Or if I give you peaks and you identify the frequencies of those peaks, you could take the difference between 2 peaks. If it's infrared, that's 2 times the rotational constant. And you could use that information and the identity of the molecule to solve for the bond length. And so those are some of the kinds of problems that I'd like to see you do. So we are out of time, but I think that's going to be a nice, concise lecture where you guys can go back and look at rovibrational spectroscopy in the IR and the Raman.